So up till now, we've seen a lot of single qubit gates like the poly XYZ gates, the Hadamard gate, and the RX and RY gates, which are basically theta degree rotation about X and Y axis. So now following the suit, we will be looking our Z gate, which is basically a theta degree rotation about the Z axis. Something cool about it is that a rotation about the Z axis essentially changes the phi angle on the Bloch sphere. And that phi angle is also the phase angle. So if we have two qubits with the same theta angle, then the phase angle basically shows the difference between them if we look at the 2 points from the top of the Bloch sphere. So from the top of the Bloch sphere, we'll see a circle, and the qubits will be anywhere on the circumference of the circle. So different positions of the circumference will basically represent different phi angles and therefore different phases. So this gate is important because from this particular gate, we can derive some other special transformations as well. So we have our Z gate, which is just like the RX and RY gates and does a theta degree rotation about the Z axis. And we have a P gate where P stands for phase and does the same thing. We'll talk about both of them. So this is the RZ matrix, and we derive it just like how we derive the RX and RY matrix by taking the Euler's formula and in the angle taking theta and Z, where Z tells us how the transformation will be and theta tells us by what angle. When we simplify this, we get the matrix that we expect. And P theta gate, which is phase gate and does the same thing, a theta degree rotation about the Z axis, looks slightly different from this matrix, but is essentially the same thing. And how do we derive it? We take this RZ theta matrix like this and multiply it with e to the power I theta by 2. So this just makes the transformation more compact. There is no change because again, this thing is a global phase. And from our previous videos, we know that global phase can be ignored. So it's ignorable. So we can keep it and we cannot keep it. It has no effect on what transformation will be there. So if we choose to keep it, nothing happens, but our matrix looks simpler and the effect is the same. So let's put different theta values and see the results. If we put theta to be pi for the RZ gate and the P gate, then it's something similar to the Z gate as is shown in this Bloch sphere. Again, I'm emphasizing we are first applying the H gate because we want to apply our Z gate on the get plus state because that is the only that is a gate on which we can visualize it as a rotation like this, and we cannot visualize it like this if our initial state is get 0, which is the default state in Qiskit. Therefore, we first transform it to the get plus state using the Hadamard gate, which we have seen in a previous video, and then see this rotation about the Z axis. Now, because the theta is 180 degree here, we see the operation to be just like Z gate as there is a 180 degree rotation about the Z axis. Now, if we put pi by 2, then this is what we get, a rotation about the Z axis by 90 degrees. And this gate is very special and has a special name known as the S gate. And if we apply S gate twice, that is a 90 degree rotation on the qubit that we have, and then a 90 degree rotation again is equivalent to a 180 degree rotation or that of Z gate, right? So now if we take pi by 4, then we get a 45 degree rotation about the Z axis, both by using RZ gate and the T gate itself. So it's a special gate known as the T gate, and applying T gate twice gives us a 90 degree rotation or the S gate equivalent, and applying T gate 4 times gives us Z gate. So S and T are special gates that we have, and our Z rotation or the phase rotation is a little more important than Rx and Ry, because we get some special gates from it like S and T, because something very crucial is changing: the angle phi, the angle that a qubit makes with the x-axis changes when we apply the phase rotation. So now tabular form to summarize all of this and look at the matrices for T gate and S gate over here. So we know that this is the matrix for RZ gate, and this is for P theta gate, and we can transform between RZ and P gate using this global phase. So when we put theta to be pi in this matrix, then we get the Z gate to be this. And when we apply theta to be pi in the P gate, we get something like this. Now we can transform between these two gates, which are equivalent and represent Z gate, by multiplying our Z gate with this particular global phase value and get this value. Now, why did we actually even do this when we know that global phases are ignorable? Because you can look, what is the Z gate matrix in reality? It is not this gate, it is this gate. So essentially multiplying this global phase gives us the real Z gate. This one is also that of Z gate, but the result that we get has a phase attached to it. And then we can ignore that phase. So instead of ignoring that phase, we multiplied something and got exactly like how the Z gate works. So this is just there, gives the same result, both of them, but this comes with the phase. If you're not able to understand what I'm saying, there is some code related to this as well and is mentioned in the description, and you can check that out. When you apply this on, say, ket plus state, then you don't actually get ket minus state. There comes a phase with it. But this works just like the Z gate, is equivalent, in fact, to the Z matrix, and therefore we like this phase matrix as well and like to multiply this ignorable global phase here and take it into consideration so that in later stages our global phases do not show up, right? So now if it's Hermitian or unitary, we know yes it is, because we have established this fact in our previous videos. Now the special gates that we talked about and saw in the rotation with the S gate and the T gate. So now if in this matrix we put pi by 2, we get this matrix. And if in P gate we put pi by 2, then we get this. Though this is useful, but this one comes with the global phase that we will be ignoring later on, and this one does not. Therefore, P gate matrix that we get here is the official definition of S gate. And to know if it's Hermitian or not, we take its conjugate transpose. And because we have an imaginary part, the sign changes. And for the first time, the S gate and its conjugate transpose are not equal. Therefore, it is not Hermitian. But still, their product gives us identity matrix and is unitary. So this S dagger is basically the S inverse. If you want to nullify the effect of S gate, just apply S dagger after it. And essentially, if we apply S gate twice, we get Z gate, like we've seen in rotations. But if you want to see it more mathematically, like we've been seeing in the previous videos, then you can refer to the code mentioned in the description. And just like the S gate, if we take the angle of rotation about the Z axis to be pi by 4, we get the T gate. And again, you can see the one that we get from RZ matrix is so complicated compared to the one we get from P matrix because of the global phase story that we're talking about. The result that the matrix from P gate gives us is free of any global phase, but this one comes with the global phase, so we'll have to ignore it over here. So therefore, this is sort of the more definition oriented and more accepted version of the T gate, though both of them are applicable, there will just be a phase difference and global phases are ignorable. Sorry, I'm repeating myself over and over, but this fact is really important, that global phases can be ignored, and after ignoring whatever the result is, if the results are same, then essentially the effect of those two gates are the same. And why can we ignore global phases? This we have seen in a previous video, but if you want a good analogy for it, then you can imagine there is a race, and if it does not matter where everyone starts from, if everyone starts from the same place, if everyone starts from 0 position in a race, it's okay, because now the relative phase will be of importance. But if everybody starts 1 meters ahead or 1 meters behind from the starting point, it has no effect, because in the race, you will be looking at the relative position of the racers to know the winner. So the global phases are ignorable, but the relative phases are not. Therefore, we can ignore the global phases, like I've been talking about it for so long now. So now, consider this matrix to be the definition of T gate, and when we take its conjugate transpose, so you see this imaginary part in the angle, in the power of E, that gets negative, and what we get on conjugating and transposing is not equal to the T gate. Therefore, T gate is not Hermitian. But still, if we take the product of T and the T gate, we get identity matrix, which means that T dagger is basically the inverse of T gate. So if you have applied T gate and want to nullify its effect, you have to basically apply T dagger, which is this equation. Matrix. And if you look at the two, they are exactly the same with just a negative angle. So till now, all the rotations that we have seen were clockwise. Therefore, they were positive. We could have get the same results by rotating in the opposite direction, the negative one. So for that, it is the same angles, you just change the sign and you get the anti-clockwise motion, right? Like we have been seeing Z gate, and it's a 180-degree rotation about Z axis, but in the clockwise direction. If you take the angle theta 180 degree to be negative, then it will be in the anti-clockwise direction. So T gate does exactly the same thing, but in the opposite direction. That is what the sign change over here means. And therefore, T gate and its conjugate transpose with this negative angle nullifies the effect, because if you go clockwise by 45 degrees and then go anti-clockwise by the same amount of degrees, the actual effect on the qubit state would be none, right? So yes, T gate is not Hermitian and it's still unitary. And till now we've seen unitary, that basically we take the matrix that we have and we multiply it with its inverse and we get I matrix, and it means that nothing happened. If you had a qubit in a particular state after applying the gate and then its inverse, it's still in that state because nothing happens. So we also have an I gate, which is basically the identity matrix. And what happens when we apply it? Nothing. It does nothing. So if you have a particular state and apply I gate on it, it remains the same. So that's all for this video, and I'll meet you in the next one. Thank you.